course. Let's see here.
We have enough people, or we have little. Enough is the wrong word. We have the right amount where we sit.
Yeah, I'm just joking. Anyway, I'll begin with a word of prayer. So, dear my Father, we thank you for this day. Again, I thank you for your creation, which you allow us to enjoy, and we just pray that you be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so I was talking about complex functions, and so a function of the complexes well, that means it's a function from the complex numbers to the complex numbers, right? So like generically speaking, we're talking about a function which is from some subset of the complex numbers, right, to the complex numbers. And we write f is equal to u plus iv, where, and you know, the u and the v are the component functions, right? Component functions of the complex function f. All right. Now, when we do pre-calculus, we learn a lot about functions by their graphs, right? And we just can't do that here now, right? Like, for example, if we look at f of z equals to z squared, right? And then we were to try to visualize that. So first of all, by default, the domain is the whole complex plane, right? And we can study what that does. Let's see here. So that's x plus iy squared, which is x squared minus y squared plus 2i xy, right? So my u is x squared minus y squared. My v is 2xy. How do you visualize this? You see, is the question. And so what's typically done is we think about a z-plane and a w-plane. All right. So we start with a z-plane, and we think about the output over here in a w-plane. All right. So the w, typically we use u plus iv for coordinates over here, and z x plus iy, right? And then we'll think about the function going from here to here. Then the question is, how do you understand a function? Like, what do you want to look at? All right. So there's a lot of different things we could look at. Let me suggest we look at a sector. What's a sector? So somewhere in here is the origin, right? Let's say it's here. And I could go like from this angle to that angle, you know, and maybe from here to there, right? So this would be something like, this is the sector I'm looking at. Okay? And so geometrically what you're talking about is like theta 1 less than or equal to theta less than or equal to theta 2, and modulus of z, well, let me say it this way, r1 less than or equal to modulus of z less than or equal to r2, right? So if we think about a typical point in here, right, z, we have z is equal to what? Like r e to the I theta. And if I replace this z with, I'm thinking of this as being the r, right? For that expression. So as my r ranges from the minimum to the maximum value, and my angle ranges from theta 1 to theta 2, I'm tracing out a sector, right? It's a portion of a circle. And then we can study, where does that sector go to under the square map, right? And so how would I figure that out? Well, I feed a typical point into my map, and I see where it goes. My map says square it, right? Right? And then we square the polar form. What do we get? We get ourselves an r squared e to the 2i theta, right? And so we'll have the situation over here that r1 squared is less than or equal to the modulus of w is less than or equal to r2 squared. And we'll have the situation that 2 theta 1 is less than or equal to the argument of w is less than or equal to 2 theta 2. That's what's going on here. So, in other words, this is the, so like, let's for the sake of like picturing, we could think about, well, I don't know, you guys tell me, do you want to let the inner radius be less than 1 or greater than 1? Greater than 1. Okay, if it's greater than 1, when we square it, it's a number even bigger, right? So if this is the origin here, and this is the origin here, then like when we square it, it's further out, right? And I should be careful. See, this is theta 1, so it's going to be more like, I don't know, like up here. So it'd be something like, I don't know, this is very, you know, like qualitative, but it would be a bigger sector, right? Its inner radius is the square of the radius of this one, and its outer radius is the square of that one, and the pi, right? If this is delta theta over here, let me put the origin here. This would be 2 times the delta of theta, right? It's taking the sector, and my picture's not very good, but it's taking the sector and it's expanding the angle of it. The square function doubles the angle of sectors, right? That's what this calculation shows. Yeah? So we could do that. We could, like, you know, describe a particular subset of the z-plane and then do the formula to it and see what the corresponding inequalities are for the w. And that would be one way we could understand what the mapping does, right? Another thing we could do would be to look at specific curves in the z-plane, right? And see where those map to. And we could study like how curves map under the map. There are lots of different choices here. There's no one answer to understanding what's the geometry of a complex function, right? It's a more it's a much more nuanced question than like what's the graph of a function. You just graph it, right? I can't just graph these because I don't have a 4-dimensional space that we can all see. Yeah. So I'll look at the graphing line idea for our next function. Our next function here is the complex exponential. All right. So definition. If z is equal to x plus iy, as usual, then e to the z is equal to e to the x times cosine of y plus I times the sine of y. That is the complex exponential. So, and of course another formula you could write here, equivalently, we could just write that e to the z is e to the x times e to the iy, right? That is e to the x times e to the iy. Yeah? This right here is e to the iy. Okay? And we can prove properties of this, like properties of the exponential are many. So like e to the z times e to the w is e to the z plus w. We can prove that. E to the minus z is equal to 1 over e to the z. That's true. All right. What do you think e to the 0 is? So e to the 0 is, yeah, 1, right? So e to the 0 plus I times 0, let's work it out. That's e to the x equal to 0 times the cosine of 0 plus I times the sine of 0, right? Which, as you guys told me a second ago, is 1. Great. What are the component functions, right? If we look at this as, you know, u plus iv, what are my component functions here? The real part of the exponential is e to the x cosine y. The imaginary part of the exponential is e to the x sine y. Those are the component functions. All right? What else can we say? What's the magnitude of the exponential? So that would be the magnitude of e to the x times e to the iy. Remember that the magnitude of a product is the product of the magnitudes. So we have the magnitude of e to the x times the magnitude of e to the iy, right? Now e to the x is a positive quantity, right? So the magnitude of that is just itself again. And the magnitude of e to the iy is 1, right? So the magnitude of the complex exponential is simply the exponential of the real part of it, like that. So is the complex exponential ever 0? We have a theorem, right, that the length of a complex number is 0 if and only if the complex number is 0. So is the length of the e to the z ever 0? It's not, because e to the x is never 0, right? It can get arbitrarily close to 0, but it can't get there. What else could, okay, so let's look at that question of mapping now that we have our bearings here. So let us look at the, I moved the camera already. So let's look at the z-plane here. And I'll look at the w-plane over here. And we'll look at the complex exponential map. Let's try to understand it. So it turns out that it's kind of nice to look at, I'm trying to think, I think I usually use, what I do? Vertical lines and horizontal lines as inputs. That's a nice thing to do. So if we look at a typical horizontal line like this, right? That would be, so I'm saying this is at y equals to y naught, let's say, right? So what's the formula here? Z equals to what? We could do z equals to t plus I times y naught. That is a parameterization of a horizontal line, where I use parameter t, right? Where does that line get sent under the complex exponential? Simple matter. We just feed it to the complex exponential and see what happens. So f of t plus I y naught is equal to e to the t plus I y naught, which is equal to e to the t times e to the I y naught. All right? So if I put the origin over here, like there, all right? And let me put the, for the sake of reference, let's put the unit circle here, okay? If we were to look at the particular point that comes from like t equals to 0, suppose this is where t equals to 0 is, right? In other words, that's where z equals to I y naught is. Yeah? Where does that point map to? Well, that point maps to just e to the I y naught, which is a point on the unit circle, which, I mean, I didn't really tell you what y naught is, but just for the sake of illustration, let's suppose that y naught's about like right there. In terms of like the standard angle, maybe y naught is pi over 4. Okay? And then, so what happens as t goes to minus infinity, what happens? This line goes to what? As t goes to minus infinity, this gets closer and closer and closer to 0, but never gets there, right? So this business over here, as we go to minus infinity, that all maps on to like this right here. Yeah? And what happens with t positive for this line? These guys, as t goes to infinity, yeah, that goes on out, on and on and on, right? That was supposed to be a line. Sorry, it's a little bit janky, a little bit crooked. As far as I can tell, janky means crooked. It's not really a word of my generation, but as I see the word used, it seems to mean crooked. So there's what a horizontal line looks like, right? This horizontal line maps to a ray from the origin. And if we were to do more, right? If we were to do like a line like this, and a line like that, and a line like that, right? What are they going to do? They're going to do the same thing, right? They're going to give us rays to infinity, right? So you can draw as many as you like. What happens though? Like if hypothetically this one is at, for the sake of discussion, let's say that's pi over 4, right? what happens once I get far enough up here, I start mapping back where I got to already, right? Like once I get up to pi over 4 plus 2 pi, that horizontal line maps to the same ray again. Same story. If I go down and I keep mapping horizontal lines down, eventually I'm going to start covering the rays that I already covered again, because they'll lie on the same geometric ray, right? So let's put that in the words. So we can cover the W plane with a strip, horizontal strip, and we just need like, you know, of height 2 pi. That's the probably simplest way to describe it. If we have a 2 pi strip in the horizontal, right? If you have a 2 pi strip, a horizontal strip, you're going to cover the whole plane over there, because as you go vertically over 2 pi, your y naughts are ranging from 2 pi to 2 pi plus 2 pi, which geometrically gets you to every possible ray. All right? So what that means is that the complex exponential is not one-to-one, right? It's not covering the codomain once. It's covering it how many times?
Infinitely many.
Yeah, infinitely many times. So if I was to look at the inverse image of like one point here, there's a countably infinite set over here which all maps to that one point. And that all comes back to the equation e to the z plus 2 pi I, let's say j, is equal to e to the z for j in the integers, right? There's this 2 pi I periodicity of the complex exponential. And that is stemming from the 2 pi periodicity of the imaginary exponential. So, okay, so then what? Well, what else would you look at? Maybe vertical lines, right? So look at vertical lines. If we do that, I get another marker. We'll use this hideous Carolina blue. So this horizontal, vertical line would have the formula z is equal to, say, x naught plus it, right? That would give us a parameterization of a vertical line, because I fix the real part, and I allow the imaginary part to vary with my parameter t. That's a parameterization. And of course it goes up, right? And so if I feed f of x naught plus it into this, I get e to the x naught times e to the it, right? And what is that? So the output, as t varies, what's the magnitude of this output?
E to the x naught.
Right. So in other words, every output of this has the same distance from the origin in the W plane, right? What do you call a set of points that is the same distance from the center point? It is a circle. So this is a parameterization of a circle of radius e to the x naught. So it would look something like this. And then you can keep doing this, right? If I was to do another one somewhere in here, I don't know, whatever. I'm not doing this to, you know, this would be, so maybe this one has radius e to the x naught, and this one maybe has radius e to the x1. So I'm doing a couple different things here. The one is trying to get you to understand what the complex exponential does. By understanding what it does to lines, horizontal and vertical lines, you get a sense that it's doing what? It's like, it would take a square grid here, right, and like morph it into some kind of sector over there, right? Or maybe a circle, maybe a pie. It depends on how big the grid is, whether or not it's going to go all the way back around, or if it's just going to be a sector. But the complex exponential will take like a rectangular grid and map it to a sector over here, actually. The other nice thing about this example is I've now told you how to parameterize horizontal and vertical lines in the complex plane. It's very simple, right? How do you parameterize a circle in the complex plane? So if you want a circle, so say center z naught, right? What's the equation of a circle in the complex plane? The equation of the circle, we could do this, right? Z minus z naught equals to r. So this is kind of off topic, but it'll help you with the homework. So what I wanted to talk about was this formula gives us the distance from z to z naught, right? So I'm saying all z that are equidistant from z naught, that's a circle, right? So this would be the equation of a circle in complex notation. How would you parameterize a circle? Simply this, right? You just write z is equal to z naught plus r e to the it. That is a parameterization of the circle. Because what it does is it goes to the center of the circle, and then it goes a distance r out from the center, and then that e to the it rotates around. So that's a simple way to build the parametric formula for a circle. We'll need that later in the course. It'll be a while before we get back to it. If you wanted to explore how maps map circles to something else, then you could feed the complex map this and see where it takes it. If you wanted to understand how a circle maps under the complex map. For example, I guess this is example. That is example 1. This is example 2, isn't it? So here's like example 3. Check this out. We'll do something really easy. Power map. F of z equals z to the power n, right? What does that do to a circle at the origin? A circle at the origin, we have z equals to r e to the it, right? So f of r e to the it is equal to r e to the it to the power n, also known as r to the n e to the nit. You're like, no, it's not it, it's int. Some others of you are like, no, it's tin. We can all agree. You can put the I wherever you want. I don't care. All right. Similar comments apply to linear algebra. I will allow you to write scalar multiplication on the right, although technically if I was a purist, I would insist it be on the left. But anyway. So what is this? So this would be in the W plane, right? We map a circle in the Z plane. This is my W equals to that. We can visualize it that way. It's a new circle, right? And if this one had 0 less than or equal to t less than or equal to 2 pi, let's say, so that means we're wrapping around the circle once. Well, the image now has radius r to the power n, right? So if the radius of the circle is less than 1, it's shrinking it. If the radius of the circle is 1, it's fixing it. If the radius of the circle is larger than 1, it's blowing it up. And in all these instances, it's taking the number of times, and rather winding once, now it's winding n times around the origin. This is very easy to see using polar coordinates. If I was to instead go, oh, Professor Cook gave me this binomial theorem in the homework, I should use it here for this problem. I should expand z to the power n into its real and imaginary parts. And then I should try to find the Cartesian equation of the circle. And then I should feed it somehow into this formula and understand how that interplays. That would be a very much more complicated way of coming to this understanding. So like having multiple viewpoints is important. There's a right tool for a certain job and another tool might be very, very wrong. Anyway, so simple example, but you know how to make this simple example much more complicated? Don't make the circle at the origin. Then it's much messier. What does the nth power map to a circle off the origin? I wouldn't start that in class. I don't know what happens. I can tell you this: if the circle happens to go through, well, no, I'm not going to do it. I'm not going to do it. I'm not going to do it. Wouldn't be prudent. Sorry, that was a George Bush Sr. joke I was veering into. That's definitely before your time. Something better left forgotten. All right, let's see here. So, all right, consider this. We have e to the z equals to w. All right. Actually, let me flip the script here. Let's say we have e to the w equals to z. I want to solve for w. Can we do this? Natural log. These are complex variables, my friends. You do not have the life experience to make such a request. And even if you did, well, anyway, calling it natural log, that's them fighting words. But you got the right idea. If we knew what the logarithm was, we could just, I mean, yes, we'd like to say w equals to log of z, right? But we don't know what that means. So let's work through it. We can work through it, right? So if we've got w is equal to u plus iv, right? And z is equal to, let's say, well, r e to the I theta, yeah? Just to put it in polar form, yeah? Can we solve this? Well, let's look at it. We've got e to the u plus iv is equal to r e to the I theta. Okay, let's use the definition. This is e to the u times e to the iv is equal to r e to the I theta. This equation gives me two things immediately, right? Because one of the things that I'd like to have just as a principle in here is if we have two polar forms equal, what does that mean? That means the magnitudes must be equal, right? Two two-dimensional vectors are equal if and only if they have the same lengths and the same standard angle, right? If you don't like that, take the magnitude of this equation. We immediately obtain e to the u is equal to r, right? Okay. On the other hand, we do not get v equals to theta, right? What do we get? We get, well, I guess we get v is equal to theta, possibly plus 2 pi j for some j and z, right? There's more than one solution there because of the 2 pi periodicity of sine and cosine that are built into the imaginary exponential. We have to face that music there. It's there. Our goal at the moment is to solve for w. We would like to find formulas for u and for v. Looks like we already found a formula for v. Here it is. Yay. What's the formula for u? Now, I will take your comment. What did you say I should do? Take the natural log. See, that's allowed here because this is real. It's a real exponential, and it's a real number. This is pre-calculus. Plain old garden variety, u equals natural log of r. It is no longer the case that we can conflate, that we can confuse, that we can combobulate, whatever. This and this are not the same. Which is, incidentally, also not equal to this, as I will soon explain. All right? These are separate notions in here. Okay, but here we go. Put these together. What you got? You got w is equal to the natural log of r plus I times theta plus 2 pi j. All right? Or to go back, let me just kind of go back and let me take us out of the r theta notation and use the principal argument notation instead. So what we've got is w is equal to the natural log of the magnitude of z plus I times the principal argument, let's say. We can choose that for theta, right? And then we've got plus 2 pi j. Right? Or you could say this, w is equal to the natural log of the modulus of z. I mean, this is a set of values, really. So I guess what I really should say is w is an element of this, I'm sorry, excuse me, my bad. I have the j here, so the equality is right, but it says for some, for j and z, right? For j and z. It's fine, it's fine. And I'd like to say that this is just equal to natural log of z plus I arg of z, all right? But to be fussy, what I really should say is that w is an element of this, because that is a set. Don't do that. Okay. This is log z. Log z is a set of values. All right? And it does give us the complete solution set to the equation e to the w equal to z. But it is nevertheless a multiply valued function, right? So definition, principal log of z is equal to the natural log of the modulus of z plus I arg of z for z in the punctured plane. This is the so-called principal logarithm, right? The little log is the principal argument plus all other quote-unquote branches of the logarithm. And you could obtain other branches of the logarithm by swapping out this argument for like arg sub alpha. We'll learn that this logarithm is discontinuous at the negative real axis. All right? There's an angle jump at going from minus pi to pi. So this function is discontinuous on the negative real axis. If instead of building this with the principal argument, we built it with like arg sub alpha, then there would be an angle jump at angle alpha, and it would be discontinuous there. So we can only get the logarithm, a logarithm or a branch of the logarithm to be continuous on a slit complex plane, which is a complex plane with like one ray removed. I have a notation for this in the notes. I call it like C upper alpha, that the complex plane with the alpha ray like deleted is what that means. Yeah.
Is that complex to the x, or is that supposed to be star for it being non-zero?
I think that, yes.
Yes?
That is my non-zero notation.
Okay, got it.
Yeah, I mean, some people do star there, that's true.
Okay.
If there's ambiguity, we could just say C.
Yeah.
There you go. Okay, so let me do a simple example of this, yeah? So example 4. If we had, say, log of 1 plus I, that's a reasonable place to start. So in order to calculate the logarithm, you need to know the polar form. Everything's polar form, isn't it? Oh my goodness. You know what? We do have like, I don't know what's prerequisite for this class, like Calc 3. But the truth is we should have like a trigonometry prerequisite because it matters more, at least for a little bit. Anyway, so this is square root of 2. And that's e to the pi I over 4. And now I can calculate the logarithm, see, because that's the natural log of the square root of 2 plus I times pi over 4. There you go. That's it. In contrast, the little log, the wee little log of 1 plus I, sorry, I'm an idiot, but you probably knew that before you signed up for this course. I mean, it's on YouTube. It's easily researched. Pi over 4 plus 2 pi j which you could also write, if you prefer, as follows. Natural log of the square root of 2 plus I pi over 4 plus 2 pi I z. It is a set of values. So typically a question I have on the test is to calculate the values or the set of values of this list of things. And in that list of things, I'll have some principal arguments, I'll have some principal logarithms, and I'll have some little logarithms. All right? And there are a few different things in here that are multiply valued. This is one of them, yeah. The reason it's multiply valued is because the exponential is not injective. It covers the W plane infinitely many times. And so if you want to just select one of those infinitely many times to pick a local inverse for, then that gives you one of the branches of the logarithm, basically. So, any questions? We raised 3 questions about our complex functions, right? Like, what are the real and imaginary part? What's its magnitude? And then the harder question was like how to invert it. All right. So I've introduced the complex exponential as a method to invert the exponential. Like, the other way around is also true. If you were to calculate e to the log of z, you get the set containing z. Because if you have something in log z, you're looking at, e to the natural log of the modulus of z, right? Plus I times theta, where, I have z is equal to modulus of z e to the I theta, right? And if you look at how that calculation goes, you've got e to the natural log of the modulus of z times e to the I theta, which is equal to, well, it's equal to modulus of z e to the I theta, right? Which is just z again. And that is true for any z in little log z. So you're like, so understand, this is a set of values, and if I take a function and I feed a set of values into the function, the output is again a set of values. All right? That said, I'm probably not going to take points off in here if you just wrote this without the curly brackets. And this is a common abuse in complex variables, is to confuse the set with its elements in this regard. All right? So if I do that in a solution somewhere, my apologies, but So the little logarithm and the exponential are inverses in this sense. We do have to think about sets of values. If I limit it just to the principal logarithm, it is the inverse for the exponential restricted to a particular strip, a particular horizontal strip. Which horizontal strip? The horizontal strip that goes from minus pi to pi in the vertical for y. See, because those are the standard angles that feed into the principal logarithm. So like the big logarithm is an inverse to the exponential if we restrict the exponential just to the strip that is, between plus or minus pi in the vertical sense. All right. Anyway, yeah. So the other question is, what are the u and the v here? It's kind of like right in our face. See, this right here is the u, and this is the v, right? So the real part of the logarithm, complex logarithm, is the natural log of the modulus of z. The imaginary part in the logarithm is actually the standard angle function. If you want me to write a formula for that, it's inverse tangent of y over x when x is positive. It's pi over 2 if x is 0 but y is positive. It's minus pi over 2 if x is 0 but y is negative. And then it's something else in quadrants 2 and 3 where x is negative. You can't just use inverse tangent of y over x because it's the standard angle. The formula for standard angle is actually somewhat complicated if you try to write it down. It would be a good exercise for you guys to go look that up and write it down. I think that's all I got to say about logarithm. Let's go on. We'll have more to say about it as we go on, of course, but that's its introduction. So I think at this point we should go back and talk about sinh and cosh and cosine and sine, right? Let me see how much time I got. Hey, it's good. I'm glad I gave myself 3 days to talk about this stuff this semester. I think I've tried to fit this stuff into 2 days in past semesters, and it was unpleasant. 3 days is good. Too little. So try this out. On your paper, write e to the I theta equals to cosine plus sine, I sine, and write e to the minus I theta equals to what it equals to. Let's see what we get. So e to the I theta cosine theta plus I sine theta, right? And e to the minus I theta cosine theta minus I sine theta. How do I know the minus appears here? Cosine is even, so it eats the minus. Sine is odd, it spits it out. Right, so I'm using the even and oddness of sine and cosine respective. Take these equations, right, and add them. What do you get? We get twice the cosine, yeah? Subtract them. What do we get? I heard a 2i sine theta. Very good. Therefore, what do we find? This gives us cosine theta is 1/2 e to the I theta plus e to the minus I theta. And this gives us that sine theta is 1/2i e to the I theta minus e to the minus I theta. If you take calculus with me, I will teach you these in calculus. The reason I teach these in calculus is they allow us to do all manner of trigonometry with algebra. I'll show you an example of this. Suppose you want to find the formula for multiplying, I don't know, cosine A and cosine B. How's that go? Excuse me, sine A and sine B. What's the formula for taking the product of sines?
It's sine times sine A times sine B minus.
Well, let's find out if you're right. So 1/2i e to the IA minus e to the minus IA. My point is you don't have to remember it. You can derive it. That's the sine of A. This is the sine of B. And then this gives me minus 1/4 e to the IA plus B plus e to the minus IA plus B minus e to the I A minus B minus e to the minus I A minus B, using the laws of exponents. I've got two A plus B's, I got two A minus B terms, and I want to write them this way because then I can pull a half out, and then I got 1/2 of, like e to the I A minus a B plus e to the minus I A minus a B minus 1/2 e to the I A plus B plus e to the minus I A plus B. Great. Close big parenthesis. We just need to know what time it is. It's cosine time. So this is 1/2 cosine of A minus B minus, parentheses here, cosine of A plus B. And that is how you multiply sines and convert them into a sum of the cosines of the difference in the sum of their angles. I derive this with algebra. I needed to use this for problem 20 in the book, by the way. Problem 20, yeah. The simplifying the right-hand side, the 1 minus z to the power n plus 1 divided by 1 minus z, that's the hard part for me anyway. Okay, anyway, just wanted to give you guys a little slice of this because I think it's really cool. And so this motivates why. So what's the definition of cosine and sine in the complex sense? What are we going to do? So to define the complex sine and cosine, I'm just going to do a little erasing here. Instead of, I just make this theta a z. And that defines cosine of z. And this defines sine of z. Just like that. So there you go. That's complex sine and cosine. So there you go. That's the definition of complex sine and complex cosine. We use the imaginary exponential to define these things. You can check some elementary things, like what's cosine of 0?
Well, 1.
1, yeah. But you worked it out. You just didn't say it, right?
Yeah.
Yeah, okay. Sine of 0 is 1 over 2i times e to the 0 minus e to the 0, also known as 1 minus 1, also known as 0. Sine of 0 is 0. How about like pi over 2? Cosine of pi over 2 is e to the I pi over 2 plus e to the minus I pi over 2. E to the pi over 2 is I. E to the minus pi over 2 is minus I. I plus minus I, 0. Cosine of pi over 2, 0. Sine of pi over 2. Again, I get I minus a minus I, which is also known as 2i. 2i over 2i, also known as 1. So this is working very nicely with regard to like real. Of course, that's not surprising because I just derived this formula for real theta, right? And I'm checking real thetas to show that it works. Well, great, not surprising. But this is, in fact, a definition for complex sine and cosine. There are other definitions which could be given later in terms of power series expansions, and those definitions are good, but they'll reproduce these. So these are good transitional definitions because we can make them now without knowing the totality of complex power series, right? So you don't want to wait until like the 70% mark in this course or something to have sine and cosine, right? You'd like them to have them now. So now we got them. Similar comments apply to the complex exponential, right? Like there are proper power series definitions of all these functions, and rather than waiting to give you those definitions, I'm just giving you these nice transitory algebraic definitions that we can work with. All right. So things you can prove. You can prove that the cosine of z plus w is equal to cos z cos w minus sine z sine w. That be true. The sine of z plus w is equal to sine z cos w plus cos z sine w. I'm sure some of these things I have you work out in the homework eventually. I'm just going to state them as if they're true by the authority vested in me by this whiteboard. So, yeah. So then the question is, what are the real and imaginary parts of sine and cosine? Yeah? So let's look at that. Like, let's work on sine. So sine of z, right, is the sine of x plus iy. But I can use the adding angles formula to work it out. So this is going to be like sine of x cosine of iy plus the sine of ix oh man, es no bueno. This is not the way to go. I'm sorry, I have forgotten the way. This is not helping. No. Let's not do it this way. This can be done, but it's like, no, let's not do it that way. So, because I need to know too many things we don't know yet is the problem that way, all right? So I guess we probably should just work with what we have, right? Which is 1 over 2i and e to the z, e to the I z, right? So we have e to the I x plus iy, right? Minus e to the minus I x plus iy. I probably should just look at my notes. That'd be smarter. Oh, this is what I did. What do you know? Duh. All right, so what we got here? 1 over 2i, and we've got what? E to the ix, e to the what? Minus y, minus e to the minus ix, e to the y.
Would it be plus y because I never minus that?
right? It's good.
Yeah, I was switching them.
I almost did the same thing myself just now. So, by the way, if you want to flip the I upstairs, well, we're going to leave it downstairs, and the reason is that I'm going to expand this. This is what? This is like cosine x plus I sine x. So some of you I've kind of talked, I've talked down using sine and cosine, but there is a time and place for it, and that's right now. Yeah? Like I do need to expand back into sine and cosine to see what's going on here. And I'm doing that. And the reason I'm doing that is because now I can collect things and look at the real and the imaginary part, right? So like the real part, rats. Tell you what, I'm going to make things a little bit simpler here. I'm going to trade this 1 over 2i for a minus I over 2. This is a fun fact for you. Since I times I is equal to minus 1, this means that 1 over I is equal to minus I. So I trade this for minus I. And then I can kind of just do math here. So I get 1/2 sine x e to the minus y, and also a minus sine x e to the y, all the half there, and then plus I over 2. I'm going to put a plus out there just to make it confusing. Because, you know, why would I mean, I'm trying to confuse the students, right? That's my goal. So I get a sine x. You're like, mission accomplished. Like, well, thank you. Sine x e to the y. Wait a minute, where'd my cosine go? Oh, that's where it's supposed to be. Dummy. Me, not you. Cosine x minus minus give me plus. And then over here, then I get a minus cosine x e to the minus y, I think. Yeah. Yeah. We can clean this up. See, this is really 1/2 e to the, oh man. Is that right? Okay, fine, whatever. I'm probably doing your homework right now. This is lame. This is not in the notes. Anyway, so, hey. Well, I'm sorry if I did your homework, but this is sine x, and you got yourself I'll put a minus out here, 1/2 e to the y minus e to the minus y, yeah? And then over here, plus I times cosine x, and then 1/2 e to the y minus e to the minus y. Can you recognize what those are?
Those are cinch.
Yeah, those are sinh. So we got ourselves a minus sine x, apparently sinh y. I am suspicious of the sign here, guys, like the plus or minus. But anyway, it's what we got at the moment. So there you go. Excuse me. Yowzers. Great. Googly moogly. Yow. Yow. Whoa. All right. So well, anyway, whether or not it's a homework problem, it's a good problem to work out, to like find out, to calculate the real and the imaginary parts, like the component functions of sine and cosine. All right, so what does this all tell me? What is the modulus of sine z equal to then? We can easily calculate that from this, right? Because it's the square root of this squared plus that squared, right? Which I'm just going to write symbolically. Square root of like u squared plus v squared, right? Where this is my u and this is my v. What happens when I square that? I get a sine squared sinh squared, and I get a cosine squared sinh squared, right? So I got a common sinh squared I can factor out, and that gives me what? So I got like myself a sinh squared, y times sine squared x plus cosine squared x. By the way, notice that these are not the complex sine and cosine. This is just ordinary garden variety real sine and cosine here because x is a real variable. We know that that's 1. And we also know that sinh is the square of the sinh. What's the square root of sinh squared? Its sinh would be right 50% of the time, so I'll give you half credit for that. But no, it's the absolute value of sinh, right? So sinh could be negative. Do you guys know what sinh and cosh look like? You guys remember? Okay, good. So sinh is like a looks like a cubic. Cosh kind of looks like a quadratic that has a y-intercept of 1 and opens up, but they're exponential on both sides. When is sine z 0 then?
When y is 0.
When y is 0 is a good answer, right? Because the only way sinh can be 0 is for y to be equal to 0. Sinh is a one-to-one function, and its only 0 is 0. So that's right. Sine of z can only be 0 when the imaginary part of z is 0. And since sine reduces to the regular sine on the real axis, we can deduce from this that the only zeros of sine z are integer multiples of pi. So there's a theorem. Sine z equal to 0 if and only if z is an element of pi z. But we could also work that out. Like we could just do, set sine of z equals to 0 and work that out. And that's probably instructive to do that. All right? Like, let's do that. Let's put sine of z equals to 0. Let's work out that it has to be 0. Or, let's work out that it has to be a multiple of pi. I'll show you the steps there. There's not much. We've already got the hard part right in front of us. We did the legwork here with this stuff. So like if we say sine of z, which is this, right? It's minus sine x, sinh y, plus I cos x, sinh y. If that's equal to 0, what does that complex equation tell me? Remember, every complex equation is actually two real equations because we can equate the real part and the imaginary part. So I guess this is example 6 or something. I don't know. Example 7 maybe? I feel like this was example 6. I'm claiming this for example 6. Uh-oh, Violet no longer cares. It's not a good sign. All right, let's see here. So we have sine x sinh y equals to 0, and we have cosine x times the sinh y is equal to 0, right? The real part. The real part, the imaginary part. I could put a minus here if it makes you feel better. But the thing is, sinh of y is never 0, except 0. So if y is equal to 0, obtain solution. Since sinh of 0 equals to 0. If y is not equal to 0, then we need that sine of x is equal to 0 and cosine of x is equal to 0. But this is impossible. Can you prove that? Well, we'd have e to the ix